Hello and welcome to a new episode of How LLMs Work. I'm Kevin, and today I'll be speaking in place of Stephen as he's a bit under the weather. In the first episode, we explored the pre-training stage of LLMs and how massive data sets are filtered and cleaned before ever being used by the model. Today, in episode 2, we're diving into the next essential step: tokenization, the process of converting raw text into a format that neural networks can actually understand. Well, before we feed any text into a neural network, we need to figure out how to represent that text and how to structure it properly for the model. Neural networks, especially those used in language models, expect a one-dimensional sequence of symbols, but they can't work with infinite possibilities, so we first have to define a finite set of symbols. Once that's done, we then represent our input data as a sequence of those predefined symbols, essentially turning raw text into something the model can work with. Let's see what Eva has for us.
Thank you, Kevin. Well, let's take a simple example. Right now, I have a one-dimensional sequence of text. It's a normal text, as you can see. Now, if we perform what's called UTF-8 encoding on this text, but wait a minute, before that, for those of you who don't know what UTF-8 is, here is a quick example. UTF-8 is a character encoding standard that allows computers to represent and store text using binary, zeros and ones. Like this example, as you can see, if you write the word hello, UTF-8 will turn each letter into a byte. So let's back again. If we perform what's called UTF-8 encoding on this text, we can see the underlying representation, the raw bits that correspond to each character in the text on this computer. That output might look like this. The first 8 bits correspond to the space character, and the second 8 bits correspond to the letter I, and so on. So actually, that's the representation that we are looking for. But here's something important to understand. While we could technically use a long sequence of simple bits or symbols to represent text, that would be wasteful. We don't want to spend precious space encoding things in unnecessarily long sequences. Instead, we need to balance two things: the size of our vocabulary, how many symbols we have, and the length of the sequence, how many of those symbols we need. So our goal is more expressive symbols, shorter sequences.
Okay, Eva, what's next? What was the purpose of that in the first place?
I want from you, Kevin, to think of each symbol not as a number, but as a unique identifier ID. In state-of-the-art language models used in production, we have to go beyond simply treating each symbol individually. Sequence length is something valuable and limited resource. To optimize this, we aim to reduce the length of the input sequence by expanding the vocabulary with more complex symbols. This is achieved using an algorithm called Byte Pair Encoding, BP. The idea behind it is to find pairs of consecutive symbols that occur frequently. For example, in our case, the sequence 233 followed by 24 appears very often. So, let's create a new symbol. In other words, let's mint a new symbol based on this, and let's say it's 256 to represent this frequent pair. Each time we mint the symbol, we decreasing the length, and we increase the symbol size. And in practice, it turns out that a pretty code setting of the vocabulary size turn out to be 100,277 possible symbol in GPT-4. This entire process of converting raw text into symbols, or as we refer to them, tokens, is known as tokenization.
So, to summarize what you said, Eva, first you transform the text into zeros and ones. Then you convert those zeros and ones into bytes, or let's say decimal numbers. Finally, the third step is transforming those bytes into symbols based on a pattern within the decimal values. Is that right?
You got it. So, let's take a look at how GPT-4 performs tokenization, converting text into tokens, and then converting tokens back into text. For that purpose, I want to use this website. It's the well-known tick tokenizer. I'll select CL100 base, which is the tokenizer used by GPT's base model. Let's try this phrase as an example. My name is Eva. As you can see, it's made up of 4 tokens. The token for my is 5159, and the token for name with a space is 836, and so on. If we delete the space, you'll notice the token IDs change. Also, this tokenizer is case sensitive, so if we use a lowercase h, for example, we'll get a different token than an uppercase H. This is how a chunk of text is broken down into symbols, and this is essentially how GPT sees the input text.
That was so clear, Eva. Thank you. So let's summarize what we discussed in this episode. We explored how large language models, LLMs, break language down by turning text into tokens. We explained how the tokenization process actually happens. In our upcoming episode, we'll explore how neural networks predict the next token from input sequences, a key step in how language models understand and generate human-like text. We'll break down how this prediction process works, what role context plays, and why it's so critical in transforming raw data into intelligent responses. Stay tuned.